Okay, let's get started. This is the last one for today. I'm George Chryssikos. I'm a physical chemist. I'm a spectroscopist doing clay science, not the other way around. Uh, how many of you have measured an ATR spectrum? And how many of you have measured the near-infrared spectrum? All right. I will be talking to you about non-invasive application of infrared spectroscopy to clay minerals. And by non-invasive, I mean that I will be talking about techniques that would let you study the sample as is, which has many advantages because you are not introducing external factors changing your sample. And quite often it means that you can collect the sample faster and you can collect many more samples in your lifetime. I'm planning to introduce infrared spectroscopy as a tool for seeing things. And I want to encourage you to see many clay samples by infrared spectroscopy, because then our brain is tuned to start developing identification criteria. We're very well geared for that. And if we have enough data that are collected in a reproducible way, then we can do a lot. So let me start with the obvious. We know that every structure has its own oscillatory modes that are characteristic of that structure. We're calling them eigenmodes, and they take place at specific frequencies, eigenfrequencies. And we detect them. One way to detect them is by resonance, because their amplitude maximizes as they absorb energy. And the whole spectrum of eigenfrequencies is linked to a material. So I will be talking about this correlation between a spectrum as an identity of this particular sample that produced the spectrum. Of course, if we are talking about molecules, we're talking about molecular vibrations, opposite to mechanical vibrations that are in the hertz range, or to acoustic that are, let's say, musical instruments that are in the acoustic range. These are at much higher frequencies. They are squeezed between visible and microwave, and traditionally, I mean, that's the infrared, and traditionally it is divided in three distinct ranges. What you call infrared generically is mid-infrared, is between 400 and 4,000 wave numbers, 2.5 to 25 microns wavelength. Between this and the visible is the near infrared, and between the mid-infrared and the microwave is a tiny slice, the far infrared. We will not be talking about that. And the common unit on the x-axis, energy unit, is the wave numbers. And the wave numbers are defined as 1 over the wavelength. Okay, let's start with the spectra. This is an infrared spectrum of a montmorillonite. This is a montmorillonite sample, and this is one type of infrared spectrum that you can collect from that. Actually, it's a near-infrared spectrum. It has to do with the units on the range of the x-axis. So this is, we don't know what it is, but this is the ID for a montmorillonite. Okay. Here are a few more spectra. If the first one was a montmorillonite, are the other two montmorillonites or not? You're not supposed to know. Don't try to answer. Is this different, sufficiently different than the previous? the green and the blue. Now you can probably say yes. Now, the three reddish ones are the three montmorillonite-rich samples from the CMS depository, Texas, Arizona, and Wyoming. The green is KGA1 kaolinite from Georgia. You see it's sufficiently different than the others. For example, you can see that there is very little in this region, in the green spectrum. And the blue, that looks like a sharp version of the red ones, is a palygorskite, or an attapulgite, as they call it. This is the palygorskite from Florida, again from the CMS depository. So, what I'm trying to say is that each mineral has a pattern, each sample has a pattern, sorry, but each mineral has a group of patterns, because in terms of chemistry, more than one minerals can fall under the class of montmorillonite, but they can have different substitutions to a different level, so their spectra will be affected. So you can make a living just by understanding, analyzing similarities and differences in this type of databases. And if that's all you need, we can stop it here. But there is really a lot here. Imagine, for example, starting a deposit in this manner. Okay, to go further, we need some more fundamentals. The classical model of an oscillator are two masses connected by a spring. And in this case, they have a characteristic frequency which is proportional to this K over M quantity, the square root of that, where K is the bond strength and mu is the reduced mass. Now, the reduced mass is the product of the masses divided by the sum of the masses. It's trying to simulate the mass of a hypothetical object that's oscillating against an infinitely heavy wall. Now, already at this very simplistic level, we have a very useful relation, because I can ask you to calculate the relative frequency between an OH dipole and an OD dipole. Now, OH versus OD means the chemistry is the same, the bond strength is the same, the mass of the H is doubling when we go to D. So you have a mass effect. And doubling the mass of the D, you will see that it lowers the frequency of the bond, if you do the calculations, by 1/3. I mean, the frequency of the OD equals approximately to 2/3 of the frequency of the corresponding OH, of an OH that has exactly the same bonding arrangement. Okay. Now, of course, this is too simple. Nothing is classical. We have to go to quantum. Quantum means quantum levels. There are discrete vibration levels. There is a fundamental level down here, and there are equidistant higher order vibrational quantum levels. And now resonance is happening between neighboring levels, and our system obeys Boltzmann statistics, meaning that at near ambient conditions, it is in the ground state down here. So most of the vibrations you will be seeing would be from this to the first. And the energy difference would be h nu, which is the wave number. H is Planck's constant. So you get a group of levels like that, assuming equidistant levels, assuming a harmonic oscillator. Now, of course, things are never harmonic, and things are rather anharmonic, meaning that at long distances, the dipole would dissociate and the two atoms would lose contact. And in this particular case, when anharmonicity is introduced, the original blue equidistant levels of the harmonic oscillator are perturbed. They're all getting lower, but the higher they are, the lower they get. So they become denser and denser and denser. They are no longer equidistant. If you look at these values expressed as a function of this anharmonicity, you will notice that, but we see it also in the graph. The graph has realistic calculations. Okay, now, with this background, we can understand a little more about this plot. Now, this plot is the full spectrum of talc, starting from the mid-infrared on the right, and the frequency is increasing towards the left. Don't ask me why the frequency is going up when we go left. It's a traditional vibration spectroscopy. Okay? And we keep the traditions. So, this is the mid-infrared up to 4,000 wave numbers. And that's the near-infrared. The red is the near-infrared. It's a continuous spectrum, but it is acquired by two different spectrometers in a different optical configuration. That's why they don't seem to match exactly. But let's look at what we're seeing here. The strongest band in the mid-infrared is an envelope of SiO stretching modes. That's from the silicate SiO part of the layer. Okay? All the rest in this spectrum is coming from the structure OH groups, the OH groups that remain decorating the octahedral sheet. Now, this is talc. This is the simplest clay mineral, the clay mineral with the simplest vibration spectrum. Why? Because it has no charge-generating heterovalent substitutions. Therefore, its charge is zero. There are no compensating cations, and it is anhydrous. Okay? So all this, it's mostly flat, as you see, but you see peaks. This is the stretching of the structure OH. This is down here at 660 is the bending of the structure OH. And then you have a suite of bands up here, which are derived from this. They are higher order bands. That is, they are, okay, this is the stretching. This is the first overtone. This is the second overtone. That is from the 0 to the first level, from the 0th to the second, from the 0th to the third. Okay? Are we still together? Okay. You notice, if I go back, is that as we go higher and higher order, the intensity goes down and down and down. But if you have enough signal to noise, you could see that the structure and the details remain the same as we go up the progress of the overtones. In addition to the overtones, there is a number of sharp peaks here, which we call combination modes. These are combinations between the stretching and the bending, and some other bands that are at lower frequency you cannot see. So in the near infrared, we see overtones and combinations. Okay. And of course, I've marked the exact position of the overtones. And on a rainy day, you can calculate the anharmonicity of the system based on the formulas that I gave you 2 slides earlier. But we'll not do it now. Okay, you noticed that next to the main OH stretch, which is an OH group shared by 3 octahedra, all 3 occupied by magnesium ions, Next to it, and at lower energies, there's a secondary peak which persists in all the higher order modes. Okay, this is a small amount of iron 2 plus substituting for magnesium in the structure of talc. Very common in nature. And if you increase the amount of divalent substitution, we are not generating charge, we are staying divalent against another divalent, then you can produce spectra like this. Now, this is another format where the peaks look down. We'll discuss about things later. So, you see magnesium and nickel here, that's from a work of Ito in the 70s. Different ratios of magnesium and nickel producing talc containing magnesium and nickel and producing the spectral sequence that you see over there. The reason you see 4 bands there is because when you use 2 different types of cations to fill a triplet of equivalent sites, you can make 3 yellow ones, 2 yellow, 1 green, 2 greens, 1 yellow, or 4 greens. We have 4 different combinations. We call that trioctahedral quadruplet. You produce a quadruplet of bands. Now, this looks significantly more complicated than XRD. In XRD, you would still have 1 basal reflection that would depend very little on cation substitution. So you get a more complicated signal here, but the added value is that the relative intensities of these 4 components correlate with the percentage of nickel occupying the octahedral sheet of this system. And these are random statistics, the blue curves, and these are the positions of the 5 samples that you see over there, the relative intensity. So you see the agreement is excellent. So the infrared is giving you this extra information about the speciation of octahedral cations in talc. I would call this an application. Okay. Now, if I convince you that this is useful, then we can learn a little more about the instrumentation of an infrared spectrometer. Most people in most laboratories, we are using FT infrared Fourier transform spectrometers. Now, for field work, there are traditional dispersive spectrometers, but this is relatively new. Dispersive spectrometers were the majority, were everywhere until the early 80s. Then they were superseded by Fourier transform ones, and now they're coming back, the dispersive ones, as field spectrometers. The reason the Fourier transform spectrometers appeared that late is because they needed quite some computing power. At that time, their computer was of the size of a washing machine. It has smaller capacity than your mobile phone. But anyway, the idea is that if you have a Fourier transform spectrometer, you have an interferometer there. You shine your beam into a system of 2 perpendicular optical paths, and they recombine because there is a beam splitter in the middle. So if you send a monochromatic signal, a laser, the output would be a sine wave. If it is 2 peaks, that will look like that. If it is a broadband, like an infrared source, that will look like this. The good thing is that we had the mathematics from the time of Laplace, how to go from the frequency domain to the displacement or to the time domain and vice versa. So we collect the spectra in the time domain, in this domain, and then we Fourier transform to go to the frequency domain. Now, that sounds a bit weird, but there are very good reasons for doing that. The first reason is that at every pulse of the moving mirror of the spectrometer, you collect the whole spectrum at once, all the frequencies at once. So it is fast. Of course, if you need signal to noise, you will collect many such scans, as we call them. The second is that in order to resolve features that are energetically very close to each other, you need a resolving power which is increasing, in the case of the Fourier transform, by increasing the length of the moving mirror, and not by decreasing slits. If you think about it, if you want to improve the resolution of a dispersive spectrometer, you have to decrease the slits, and you have less and less light going to your detector. This is not the case with the Fourier transform. And the last is that the position of the moving mirror, which produces all these wonders, is monitored, is measured, or is clocked, whatever if you want to think in the time domain or in the displacement domain, by a laser. So it is known with the resolution of the wavelength of a visible laser. It's extremely accurately known because this is coupled to the same mirror. So your x-axis is extremely reliable without needing to do a calibration of the x-axis. Okay, now the standard type of measurement you would think is a measurement in transmission. You have your sample, you want to pass the beam through and record what is left on the other side of the sample. Okay? Now, when you do that, you collect a background, what is recorded by the spectrometer without the sample, then you introduce the sample, you take the ratio of these two, of what passed versus what would have passed without the sample, and you call this transmittance. And transmittance is the type of spectrum where the peaks are looking down. And it's the most common type of representation in the literature. I would strongly suggest that you don't use it. And instead of transmittance, you're using absorbance, which is the log of the inverse ratio. So the peaks would look up. And why would I suggest that? Because it is absorbance that shows up here in the Beer-Lambert law. The Beer-Lambert law says that the absorbance of the sample at any frequency nu equals to the absorption coefficient or extinction coefficient, which is this epsilon, which is a function of frequency, and it is characteristic of the material, times B, which is the sample thickness, sorry for the beta here, this is B, times C, which is the concentration. That means that this formula is the one that will get you to quantitative analysis. This is the one that connects concentration, number of oscillators per length, with absorbance, not with transmittance. Of course, okay, you have to calibrate that and everything, but you start with a solid law that says that absorbance is proportional to concentration for a given substance and for a given optical path. All right. If you try to apply that to a clay sample and to many other samples, the first problem that you have is that the epsilon, the extinction coefficient in this Beer-Lambert law, is very big. It's a very big number, which forces you to use a very small B thickness in order to measure, be able to measure a few photons getting on the other side of your sample. Your sample has a tendency to absorb everything. And that happens for many samples and for many bonds, if you want, including the SiO and all the modes of water, especially the stretchy modes of water. All of them are critical to the study of clays. So this type of transmission is rather difficult to apply. Instead of that, people have used the KBr pellet solution. That is, you dilute your sample in KBr, press it, make a pellet. The concentration is reduced a lot by that, 100 times, and then you measure the spectrum. Especially in the case of clays, I see problems with that. The first thing is that KBr is hygroscopic. So if your sample is hydrous and the water is part of what you want to study because this is naturally there, it's part of the clay, it's part of the history of the clay and all these things, that if it is a lot, that will dissolve the KBr, or it will be redistributed with the KBr. The second problem is that KBr is an ionic solid and the cation is potassium, and under pressure, especially in the presence of water, it could ion exchange with your interlayer cations, if you have interlayer cations. So this is not a very good technique for studying smectites. There are lists of spectra in the literature, very reliable ones, but they have a protocol of how to make samples, and this protocol involves drying the samples to rather high temperature, 150 to 100 degrees. So you keep them at low water content because only then you reduce the other problems. It's not easy to apply if you want to do it correctly. I skip diffuse reflectance in the middle if red, and I jump to attenuated total reflectance. Attenuated total reflectance is the technique with the broadest application in chemistry and also in mineralogy, in mineral samples, to study powders, pastes, liquids, not gases. That's the cross-section of an ATR cell. The beam comes from one end. There is a small prism here made of diamond in this particular case. The beam is internally reflected in the diamond prism, totally reflected, and comes out from the other side and is being detected. There is usually a press that would let you keep a powder in good contact with a diamond. You don't need a press if you have a paste or a self-sticking film or a liquid, of course. Okay, so ATR collects the spectrum from this few microns of the sample in contact with the diamond. It's a very short-sighted technique. We'll see how much this is. It is based on the fact that the sample has a smaller refractive index than your prism. So for the prism, you need an infrared transparent material with a high refractive index. Diamond has not the highest. The highest would be germanium. Diamond has 2.4, germanium has 4. The problem is that if you study natural samples without beneficiating and separating fractions, etc., the possibility to have some hard mineral there like quartz is very high. And if you use quartz on germanium, you destroy it. So diamond is expensive, but it is forever. Germanium is cheaper, but we have to change it every month. go for the diamond, except for some very few cases. ATR is not destructive for the sample. You just press it, click it, and measure it. You need a few milligrams, a few grains of sample. You don't care about the thickness because even if you have a thick sample, it's only the first few microns that will be measured. Of course, if you have a laminated structure, you see only the external ones. This is rarely the case with clays. And you can adapt it to many different experiments, as you will see later. The principle is this internal reflection that you see up there, and we call it total reflection, but this is a misnomer. A total reflection is not total. What's happening at the point of total reflection is a small leak on the thin medium, on the top medium, on the air side, or on the side where the sample will be, that extends only a few microns. And it's a standing wave. And this is the probe that will see your sample. And if you do the calculations, this is the penetration depth. If you do the calculations here, you will see that the penetration depth depends on the wavelength or on the wave number. And let's say at 1000 wave numbers, using a diamond at 45 degrees, and having a sample with a refractive index of 1.5, there you get a penetration depth of 2 microns. It's very difficult to achieve 2 microns freestanding, nearly impossible for a clay, and it's completely impossible for water. Now, of course, if I go to 3000 wave numbers, which is the upper part of the spectrum, this penetration depth will be reduced by a factor of 3, will be 650 nanometers. Okay, this means a few things. Let me get rid of this. All right, the first thing is that the sample must be in very good contact with the crystal, because optical contact, because even a micron distance would ruin your spectrum. Okay. The second is that you have to clean yourself very well. A fingerprint, the tiny amounts of fat that are squeezed out when your finger touches the crystal, are very visible. It has to be cleaned very well with paper towel. The good thing with the diamond is that you can even use sandpaper, to clean it. You can do anything, nothing will happen to it. Now, there is a catch here. The catch is that the penetration depth, which is your effective sample thickness, is changing with wave number. That means the Beer-Lambert law will still have absorbance, will still have the epsilon, but here it will have the penetration depth. And that would produce weaker bands at high frequencies than a hypothetical transmission spectrum. All the spectrometers, they have an option to make this correction automatically by dividing with the wavelength. And that's why this is what we call an ATR spectrum. An ATR spectrum is nothing but an absorbance spectrum that's compensated for the wavelength dependence of the penetration depth. I skip that. All right. So one way to overcome the problem of very high extinction coefficient that hinders transmission studies was to use ATR, which has inherently a very small penetration depth. It observes only a few microns of your sample and does not show saturation. The other way So we played with B, substituting the penetration depth of ATR for B. Now we'll play another trick. Instead of working with the fundamental modes, the stretching and the bending, let's try to do spectroscopy on the higher order modes in the near-infrared, knowing that their corresponding extinction coefficient goes down and down and down by quite a lot every time we go an order higher. So this would be the fundamental from the 0 level to the first, which is much bigger. Much bigger means factor of 20, factor of 50, depending on the mode. That's a lot. And this is than the first overtone, and this is another factor 20 or 50 to the third overtone. So that allows us to do non-invasive data acquisition, collect spectra on the sample as is. Now let's think about it. The spectrum of talc, it had a very strong SIO envelope at 1000 wave numbers. First overtone would be a bit less than 2000. Second, a bit less than 3000. Fourth, a bit less, more than a bit, than 4000. And every time the intensity would be reduced by 50. There's nothing coming from the SIO in the near-infrared spectrum. By the time the overtones, they are so high that they're negligible. So in the near-infrared, you will only see OH-related modes. It's like doing proton NMR in a sense. Coming from the structure OH groups and coming from the water in the structure, only. Without perturbation, direct perturbation, without observing the SIO part, and also without observing any anhydrous accessory mineral that may be there. Quartz, carbonates, whatever. So it's made for studying clays. The other practical application is that the fact that SiO2 is transparent in the near-infrared, that means we can collect the spectrum of a clay in a glass, which is something through the glass, which is something we cannot possibly do in the mid-infrared. There's no way. Or we can interrogate a distant sample by sending the light through an optical fiber and collecting the reflected light back. Or we can do that remotely. We knew there was water in Mars long before the vehicles, the rovers, went up there and made spot measurements. We knew that because clay minerals were detected, and clay minerals are only made, and that detection was by near-infrared, from the reflected light. Sun as a source, and we measure the reflected light. Now, in the lab, you would do near-infrared in a number of ways. In the laboratory, if you have a powder sample, you would use a powder probe. A powder probe is a bundle of optical fibers, 15, 17, something like that. Half of them are sending the light. You touch the sample of whatever object you want to measure. The reflected light is coming back from the remaining fibers and is being analyzed. The whole thing looks like the gun that this fellow is holding here, but the sample is not clay. All right. Now, if you have a coarser sample, it's awkward to measure grain by grain. And then you would use an integrating sphere. An integrating sphere works in this manner. You put the sample in a beaker with a quartz bottom, transparent bottom, which is placed off-center from the beam. And that means when this is rotating, you are sampling a circle. You are sampling quite a lot of sample there. and it's very good for heterogeneous samples. And clays can be, at this level of grain, they can be very heterogeneous. So by doing that and playing with the size of this, you can study statistically meaningful information for samples between 1 gram and 1 kilogram, whereas the other is sub-gram. And then you can do it remotely. This is an application many years ago, that's 25 years ago. This is an application over the conveyor belt. This is bentonite in this conveyor belt, and it's measuring real time without touching it. And it's reporting its spectrum, which is correlated with other things. So by that, you can measure from kilos to tons. And imagine that this is installed in an open air environment next to the sea. I mean, the beach is 50 meters from this, so high salinity and all these things. It's a very robust technique because you can seal it with windows, and you only have to dust it off from time to time, and that's it. Okay. Do you have any questions that you would like to clarify up to this point? Yes. The microphone.
For the large scale application, you mentioned that you can seal off the unit with glass, so then the water isn't an issue. Is that the actual, but the water would still be an issue on the sample itself, right? So if you had, like if you have a thin film of water on the surface of the clay, then that would be an issue. Is that correct?
I consider the water on the sample as part of the sample.
Okay.
So I'm interested in that water.
Right.
And in the following slides, you will see ways that we can study the first molecular layer of water in contact with clay in the presence of the next layers that start looking like liquid water, and they are not that interesting. I mean, I'm not interested about how much water this has. There are other techniques for that. You do a gravimetric technique and you're done.
Right.
You decide where do you want to stop at 100 degrees or 200 degrees, but that's it. I want to use water, the first layer of water, as a proxy for the surface that's sitting on.
So you can still do analysis even if there is like free water on top of it.
Up to quite a big margin.
Okay.
We could measure material in a smectite bentonite mine, at least the one that I've worked with. The natural material is about 35% water. Okay, we can measure it at that state. We get more information if we let it dry in the air and measure it at roughly 15 to 20% or whatever. But that's about it. We can see it in the presence of water. Okay? All right. Now, near-infrared, ATR already, but near-infrared par excellence is a technique that would allow you to measure hundreds or thousands of samples. And in this manner, you would be able to appreciate the richness of clay in a deposit, for example. And you collect spectra, and you collect them very reliably and reproducibly, but they're quite different from each other, and they look like this. Your screen will look like this at the end of the day. These are about 200 something spectra. I cut the x-axis, doesn't matter. This is near infrared, but that's how they look. There's a lot of information there. but we should do something in order to extract it, because there's a lot of irrelevant thing there. Okay, already at this level, there are mathematically robust ways to correlate this with properties. Now, I'm not talking about predicting properties solely from the spectra. I'm talking about having a set of samples for which properties have been measured and spectra have been measured, and I can use the spectra to predict the properties, to correlate with the properties. There's a whole ensemble of techniques there that combine statistics and linear algebra. They are called chemometrics. Today we would call them artificial intelligence, but I mean, okay, that's the early days I'm describing. If you can calibrate, you can convert this spectra that you saw in the previous transparencies to predictions for properties. And you can do separate calibrations for different properties and apply them to the same spectra and get a number. And if you collect the spectra in real time, your prediction would come in real time. Now, think about the hypothetical scenario where you are working for a company that runs a deposit, and they are doing regular analysis to their samples. They measure one sample per shift, 3 samples per day or 2 samples per day, whatever, and they have a collection of samples and independent values measured with their own know-how techniques, quite reproducibly for them. I mean, repeatable for them. They may not be reproducible because others would do some other technique, but they have a set of samples and a set of different sets of measurements. So if I manage to calibrate, to get the spectra of the samples and use chemometrics to link the spectra to the properties, which would look like this, would look like a calibration up here. Sorry for this big thing. I mean, that's... then I could collect a spectral sequence. Here's a spectral sequence. That's a recording for about 3 hours or 2.5 hours. It's recorded every 3 minutes. It's a continuous production on the production line. Actually, this is not the production line, it's the incoming material. And you can see how different properties vary. I will not tell you much about what these properties are, but I can tell you that in this way you can make predictions for properties like methylene blue score, because companies measure methylene blue, nobody else would measure methylene blue, but that's what is available. You can measure water content against the calibration values. You can measure carbonates and a few other properties. You can do some other things also. You know that the standard way of doing mineralogical analysis of a sample is by XRD. And there are many companies that do, they have an XRD routine to measure the samples and say that much, you know, smectite, whatever, quartz, mineralogical composition. And they do that by measuring the intensities of the XRD against some standard. All right. If we take these intensities as independent measurements for the presence of these minerals that they are of interest, and we calibrate the spectra against the XRD outcome, then we can make the XRD prediction faster and for more samples. And these would be calibrations for palygorskite content, serpentinite content, and smectite, which are the three main mineralogical compositional parameters of a deposit in Western Macedonia and Greece. So you see how calibration would look like. Palygorskite and serpentinite are quite well defined. This is broader, and it's broader because there's not one smectite. It's a very big variability of smectites there, but still we are doing something. And in any case, if you validate this method on a drill core that has not been included in the calibration, you get something like that. These are the layers as you go down from the top. Palygorskite in blue, serpentinite in red, that's the bedrock eventually, and smectite in green. The solid points are XRD, and open points are chemometric predictions. These are independent measurements, and these samples were not included in the calibration. Okay? Now, remember, if you apply these techniques are valid within the range of their calibrants, in the local context of their calibrants. It shows you that you can take, you cannot take a technique from Northern Macedonia and put it to Florida and expect it to perform the same, because the geological context of palygorskite in Florida is different. But it shows you that you can do the same thing, the same approach, anywhere you want and get more data. It's not a matter of stopping the XRD data. It's getting a denser collection of points. Okay, now let's increase the level of difficulty a little bit. Now we want to condition the samples, to change their humidity, to change their condition, and do that in a systematic manner and measure them in situ as we change the conditions. All right, to do that, you need an environmental cell. You need two things. In the near-infrared, the powders are fine. In the mid-infrared, in the ATR, you need the top of your surface to be exposed so you can do things from the top. That is, you want the press out of the way. If you want to get rid of the press, then you have to make a sample this way. Make a dispersion, make a slurry, put a drop on your diamond, let it dry slowly. In most cases, it will make a very nice film adhering on the diamond, and this will be your sample. And that's an environmental cell, which is nothing but a cup with an input and an output. You don't have, this is homemade, but you can do much simpler constructions. Even a small inverted funnel would work above the sample that would blow a gas that would escape. So this is over the ATR on the left. This is over the integrating sphere. This is over a high temperature cell. This is, both the near-infrared and the ATR. That's some rather scientific extravaganza. And you can have a humidity generator to produce air with controlled relative humidity to change the condition of your sample. And then you can have the same sample. This is a bentonite, it's Wyoming montmorillonite. The spectral changes you observe as you change the relative humidity from about 20% to 90% RH and staying at every step for 10 minutes. It's not in equilibrium, so that's how it looks like. So you see immediately that in the spectrum, in the ATR spectrum of the montmorillonite, there is at least this band, and to a smaller extent that band, that change in intensity, they decrease a lot when the material gets drier. So obviously this must be related to molecular water. Okay. Now, getting into smectides, let's do it a bit more systematically. Let's compare, we have seen talc. Let me put a trioctahedral smectide, that's a saponite, California from the CMS, in blue in comparison to the talc we had in the previous slide. Now, if I ask you to compare the two spectra, you would see that the SiO looks more or less the same. There is the sharp bending and the sharp stretching that we had before, that these are the structural OH groups, slightly different, but they are there more or less. But there is an envelope here of overlapping bands, and there's another band here that were not there before, and this is water. This is molecular water. Different kinds of water, starting from the one that's decorating the clay particles all the way to bulk water at these conditions. Yes, by the time you get the microphone, I continue with the near-infrared and then you ask on both. The same in the infrared, the blue spectrum has the same bands here, but it has additional bands there and here, which are due to water. So this is one level of complication. We are still trioctahedral, it's still magnesium, but now this has substitutions, it has cations, it has interlayer, cations, they're hydrated, there is water. Yes?
On the previous slide that you are increasing the humidity, you show for the stretching,
yeah,
it's increasing the intensity, but in the bending.
There is also in the bending, you don't see it very much in this sample, but there is also in the bending, if that's your question.
Yeah, but my question is more like the stretching is more sensitive than the bending.
Yes, it is. It has a stronger extinction coefficient, so any change there will be manifested quite a lot. Also, I don't want to say more. Wait a couple of more transparencies. Okay, so that was a comparison between the saponite and the talc. So we introduce water. Saponite is a smectide. Okay, let's compare a trioctahedral smectide to a dioctahedral smectide. Now you see that the water bands are similar. This one, that one, not identical, similar. Here and there. But the structural OH modes are very different. You see the trioctahedral over here, the dioctahedral higher, the same over there. Already the dioctahedral modes, OH modes, aluminum OH, aluminum magnesium OH, etc., are so high, they're sitting on the slope of the SiO modes. So that's a very broad brush distinction between dioctahedrals and trioctahedrals. The reason for these differences are, okay, in all cases we see OH groups, but the main reason is that in the trioctahedral minerals, the OH group is perpendicular to the plane, whereas the dioctahedral is in plane and it is involved in some H bonding with the rest of the plane. Okay, let me get a bit further. All right, now I'm introducing a problem that you will find in other techniques as well. In this case, because of the presence of water, we have overlap of weak structural OH bands with the bands of water. And we need to separate those. And we need to do that for a number of reasons. First of all, water can be variable, whereas the identity of our material is not variable. And we want to be able to see the layer, the signature of the layer, in the presence of a variably wet interlayer. Variably because it is in interaction with the environment. So it's a matter of resolving features due to water and structural OH. The rest of the game will be on that. The first idea, now what I'm showing up there is the OH stretching envelope in the mid-infrared ATR of a smectite. That's how it looks. It has a sharp band and then these two overlapping broad bands. You can go back in your notes and see that this is taken from there. And my first goal, my only example would be how to separate the OH groups, the structural OH groups, from the water signature there. Okay. The first approach we would use is band deconvolution. Okay? Start with 3 bands, awful. 4 bands, maybe. 5 bands gets better, 6 is perfect, but then obviously the more we put, the better it gets, but then it loses physical meaning. So we don't know how many bands are there, and a problem of the convolution becomes difficult when we have sharp bands overlapping with broad bands, because the sharp bands are represented by a few points compared to the broad ones. Okay. It's not really an alternative, but as an additional tool, I would ask you to consider observing the second derivatives of your spectra, of your absorbance spectra. And this is why this is an artificial example. It's a calculated example that has no noise. You see a synthetic spectrum, the red one up there. The red one consists of a blue component of a green component. The blue component is 50 times stronger, the area is bigger by times 50 than the green. But the green is 4 times sharper than the blue. So we have a weak, sharper green component overlapping with very strong, broader blue component. If you take the derivative, and there is also a slope, a linear slope, which is common in the spectrum. If you take the derivative of that, the derivative of the red is dominated by the sharp component. Second derivatives, if you think back to the high school years, second derivatives are extremely sensitive to the width. The sharper the bands, the stronger the second derivative. So this is a way to filter out the broad bands in the presence of the sharp bands. Okay? It's another way to observe things. We haven't changed anything in the spectra. These are the same spectra we had before, but we'll be looking additionally to the second derivatives to identify the possible presence of sharp bands. How this is done? Well, the way this is done is by the Savitsky-Golay algorithm, which says that the second derivative at a certain point here can be calculated from the curvature of 2n plus 1 points around this. It applies a function, a polynomial function, a second degree polynomial function, through a range around your central point, calculates the derivative of that point, and then moves the range to the next one. And that's how the derivatives are being calculated. Okay, but we said that the sharper the band, the stronger the derivative. Noise is sharp. So your spectra should not have much noise, else the second derivative of the noise will cover your spectrum. Okay, so the practical question is, what derivatives, how many points are we using for our derivatives in clay science? And this problem is related to what Bruno was saying, how many points you need to describe a peak, an XRD peak in his case. So it starts with what is the optimum spectral resolution in order to get a recording of the spectra of interest. And I would say that for most dioctahedral smectites, a resolution 4 in the mid-infrared or 8 in the near-infrared is fine. However, if you have trioctahedral smectites or kaulinite, serpentinite, if you're studying these, or if they are present as admixtures in your sample, you'd better go better resolution. Resolution 2 wave numbers in the mid-infrared, 4 in the near-infrared. And in some extreme cases of very sharp bands, like in talc or dikite, you would even go to resolution of 1 wave numbers. And in addition to these points, in addition to this interval, you would normally put an extra point in between for cosmetic reasons. So your delta nu, the difference between the 2 points, would be 2 wave numbers the first case, 1 wave number, half a wave number, but the resolution is twice as that. Now there is a catch here. If you want to collect a good spectrum, 100 scans for averaging at 4 wave numbers resolution, on a moderate spectrometer, you need about 1 minute. If you want to get the same signal to noise and improve the resolution by a factor of 2, set the resolution to 2 wave numbers instead of 4, you need 8 times longer. So the acquisition time will become a determining factor on how far you want to go. Okay, now, having said all that, this is the second derivative of the Montmorillonite that you saw before. And what you see here is that, for example, the bending modes that were down here, now they look better defined in the second derivative. Very characteristically, you see that the broad water bands are now very weak, and the sharp band is here. And even when you blow it up, you see that it's not symmetric. Now, you may not be convinced by this plot alone, but if you measure quite a few, you see that this asymmetry is systematic and maybe meaning something. Okay. We agreed that we need high signal to noise data for being able to do second derivative analysis. We also need to compensate extremely well for changes of the atmospheric gases inside your optical path. Your spectrometer, I mean, you may be purging it, you may not be purging it, but the spectrometer and the path inside the ATR cell will have some kind of air with a certain amount of water and carbon dioxide. And when you approach to put the sample, you probably breathe. So you may alter this water and carbon dioxide concentration. And that would produce bands that are very sharp in the spectra, especially the bands of water, because they're coupled, the stretchings are coupled with rotations. I stay out of it, but they look like noise, but it's not noise. It's the spectrum of water vapor that's not in your sample. It is in the path of your spectrometer and was not compensated by the background spectrum that you took before measuring the sample. So the one thing, the good practice is to measure very frequently background spectra. Ideally, for every spectrum, you have its own background. Even then, you may see changes. In that case, measure another background after you measure your sample. Clean and measure background. It's a good practice because you can also make sure that you leave the ATR cell clean for the next person to measure. But anyway, you can interpolate between the two backgrounds and correct perfectly the water vapor spectrum. Look at the effect of water vapor. In the upper panel here, the raw spectrum, that is, we are up here, okay? There is a blue spectrum, which is the raw spectrum, the spectrum that was collected with all these precautions by somebody who knows what he or she is trying to do. And the second derivative of the blue spectrum is the blue derivative in the lower panel. And this is after correcting for trace water, which would appear only at high magnification. It would become like the red. That is, you have a situation where it's here, it's 0.1% or less than 1% or whatever. No, it's less than 1% of the total amplitude. That's the amplitude of the water spectrum. And in the lower graph, it accounts for 25% of the amplitude of the signal. It has a tremendous effect in the second derivative. So you'd better correct your spectra and you do it the right way, the way I'm describing by measuring a post-reference and interpolating. Don't rely on routines that are on your spectrometer software that look like atmospheric gas correction or so. They're just chopping the part, but you cannot get derivatives after the operation. So you have to do it properly. Okay. Now, if you go through this hassle to get a good signal to noise spectrum and without water vapor and all sorts of things, I can argue that your effort will pay off. And this is an example. Palygorskite. Does anybody work with palygorskite? No. Palygorskite has this modulated structure that you see over there. It's a 2-to-1 zero charge mineral, but the 2-to-1 layer is discontinuous. It looks like that. And the cavities that you see are essentially tunnels because the whole thing makes a lath like a fiber. Toshi had a beautiful SEM picture of Scipiolite, which is the first cousin of this palygorskite that you see here. So this is a beautiful example of a very complex internal surface. There are tunnels, channels, edges, in addition to physisormed water. So if you take a sample of palygorskite at ambient and you measure it, this is what you see in the second derivative. And these are the structural OH groups that are there. It has a mixed dioctahedral, trioctahedral character. So aluminum, OH, aluminum, iron, this is iron 3 plus, 2 irons OH. This is the dioctahedral triplet compared to the trioctahedral quadruplet that we saw for talc in the first transparencies. Now you have two sides occupied by two kinds of cations. So you have two of one kind, two of the other kind, or 1 and 1. This is what we're seeing here. And this is the trioctahedral signature. So this is what you get. And you can use the relative intensity of these bands to quantify the amount of iron 3 plus in the octahedral sheet of palygorskite. The same way that we had it. Okay, now let's expose this sample to a breeze of dry air. very much in the way we would dry clothes in the summer. The spectrum becomes like this. If I ask you to describe it, you would probably say that all these bands I was talking about before, they've shifted. This shifted here, that there, the three dioctahedral ones went up, the trioctahedral went down. Okay, some distortion is happening because water is coming out of the tunnels, and water had some role in keeping the structure together. Now remember, this is not a smectite. They cannot move very far as hydration changes. But what is this huge thing that appeared here? The huge thing that appeared here is due to the surface silanol groups. So this discontinued structure, this continued tetrahedral sheet, silicate sheet, has to terminate with OH groups. These OH groups are hydrophilic. When they're bonded to water, there is strong hydrogen bonding. You will not see very much because the bands become broad and they're not visible. But now that the water is leaving, with very mild conditions, they appear as isolated dangling silanol groups. Keep in mind that in every time that you have or you create, like here, a dangling bond, either OH or NH or whatever, this will be very visible in the near infrared. More in the near infrared than in the mid-infrared, because the unharmonicity, it develops very high unharmonicity, and this is what makes the bands active in the near infrared. Okay, and this is a transition. You can probe all the steps from one end to the other. It's also aesthetically pleasing to record this type of spectra, and you can do many things with that. Okay, let's get back to the mess of having many spectra of smectites in their natural state, so they're bentonites. So this is the combination OH bands, these are the overtones, and this is the combination of water. The same spectra in the second derivative, they look like this. You see immediately how they get together, how you get rid of redundant broad information. Now I say redundant, but in Bruno's case, in one of his examples, that was 30% of his material, okay? But let's look at the sharp features. And you get this much simpler thing where the bending modes are here, and you can go back in your transparencies and you can compare them to the corresponding mid-infrared and so on and so forth. Actually, what you see as very sharp here, this is an impurity of kaolinite. It's a very small impurity, but it has a sharp band and produces these very, very sharp features there. Okay. Now, the last big separation technique I want you to know is due to H to D exchange of the sample. We said in transparency number 3 that if you go to an OH bond and you convert it to an OD bond, the frequency drops to 2/3 of the original value. If you can do it, that is, if deuterium can reach the OH where it is and exchange. In the case of clays, of smectite clays, of smectites, this is only possible at ambient temperatures for the interlayer. Structural OH groups would not exchange at ambient conditions. Okay, this is, look at the spectrum. This is what we had before, the bands of water, the sharp band that we are playing with and we're trying to separate. This is the part that we try to do the convolution and we abandoned it. Okay, now we deuterate and that's it. How do we deuterate? We make this thin film on the ATR window. This is an ATR spectrum. We put the environmental cell and we bubble dry nitrogen through small amount of D2O liquid. This D2O humidity deuterates the interlayer quite quickly, and this is the equilibrium. You get rid of the water here. Actually, what has moved, sorry, no, I don't want that, I want to go back. So you move all anything that could be exchanged has moved. And what's left could not be exchanged because it was not accessible. And that part is the OH. And this part used to be water and is now D2O. Surprise, you see the water has a sharp band as well. And you can do this trick to any clay and get a very detailed view of what's happening with the structural OH groups. And this is what we have here. That's a palygorskite from Greece. That's a smectite we had before. So although the water signature, the D2O signature, is not that different in one case and in the other, the OH groups are very different. They are left behind. And see how weak they were. Most of the signal that you had there was the water. This is all the yellow area was deuterated and moved to the red, to the right. And that can be done easily, can be done in situ. If you have an ATR cell, invert the funnel, bubble dry nitrogen through D2O, send it in, you will see that. And some of you are studying dioctahedral smectites, bentonites, and they know that one of their most difficult to reach properties is the layer charge. Now, this is the new OD band. This sharp band that was previously hidden there and could not be resolved, now it is resolved, and this is the band that became the basis. The position of this band was calibrated against layer charge and is now, I would say, the fastest, the most efficient. I would say also the most handsome tool for determining layer charge in smectites. More on that, session 19, Thursday morning in one of these rooms. I don't remember which one. And the name of the game is to record very accurately the position of this band. And you know 3, 4, 5 transparencies before that if you do second derivative, you can get very accurate, no, it's not this transparency, very accurately the position of this band, and that's how you measure, and then you measure the position of the band and you determine the charge. This is a type of measurement you cannot do with a field dispersive, with a non-Fourier transform spectrometer because you need the accuracy on the x-axis. You interpret shifts of 0.2, 0.3, 0.4 with numbers. Okay, so we went a long way together. I want you to know that ATR and near-infrared can study the sample, your sample as is. They allow you to change the conditions of the sample. They allow you to do reactions on the sample. You could introduce, I didn't show you, temperature as an additional variable if interested for doing reactions. You can do that in situ. So you may want to try them one day. And if you have a specific project with specific questions, don't hesitate to contact me. We cannot discuss everything in this room, but so I would call it a day. We still have some time for questions, and the rest via email. Thank you.